Hello everyone, welcome to another video of Circuit Digest. In this video, I'll show you how you can build your own 18650 charger and booster module like this one. With this module, you can directly connect an 18650 lithium cell and use this charging port to safely charge your cell. Then, when the charging is done, you can use this USB port to connect any electronic device that needs 5 volts for operation, like an Arduino board, a Node MCU, or even a Wi-Fi dongle. Interesting, right? So let's get started. Along this video, I'll tell you how the board works and also explain to you the circuit diagram. But before we get there, I should mention PCBWay, who are not only the fabricators of our PCB board but are also the sponsors for this video. PCBWay provides high quality and cost-effective PCB prototype and fabrication services. They are well equipped to handle standard and advanced PCB designs and can also provide assembly stencil and PCB assembly services. They are known for their shorter lead time and customer service and also supports the maker community. So do consider giving them a try for your next PCB. Coming back to the circuit diagram, we have two important ICs over here. One is the TP4056 lithium-ion battery charger IC and the other one is the FP6291 booster converter IC. On our board over here, you can see the TP4056 IC placed over here and the FP6291 placed over here. So both these ICs are very small, so you could have even reduced the board size further by using assembly components. Now let's see how the design is made. Now since this is a battery charging circuit, the first thing we have to consider is the battery itself. So my 18650 cell over here is rated for 3800 mAh capacity and or 3.8 Ah and 3.7 volts for voltage. So all the lithium cells will be rated for 3.7 volts, only your capacity might vary. Now the other things such as the charging current or the maximum output current are not mentioned on the cell, which we can derive from the capacity. So if the capacity is 3800 mAh, it means I can consume 3.8 amps from this cell for 1 hour. And to determine the charging current, it will be basically 0.5 C for 18650 cells, meaning it will be half of 3800 mAh. So it will be 1.9 amps. The charging current will be 1.9 amps, but I have reduced the charging current to 1 amps because I don't believe that this cell is actually a 3800 mAh. There are many Chinese cells in the market and most of them would represent a high mAh value. So to be on the safe side, it's always better to choose a lower charging current, and 1 amps is a very safe value for almost every 18650 cells. Now coming to the design section, we have the lithium-ion battery charger IC over here. So this IC will take care of the important things. So while charging an 18650 cell, there are three things which we have to monitor. One is the voltage, the other is the current, and the third one is the temperature. So for every 18650 cell, the minimum voltage that it can reach is 3 volts and the maximum voltage that it can go is 4.25 volts. So our TP4056 IC over here will take care of all those things, which we can understand by seeing the graph on its datasheet. So this is the pinout of the IC and this is the graph which can be found in the datasheet of TP4056. So as you can see, we have the charging current on the left side, the battery voltage on the right side, and the time over here. Now when the battery is connected, the minimum voltage that it can go is 3 volts. So let's say when we connect the battery at 3 volts, the charging current will start to increase. So this is the charging current axis. So the charging current will directly go above 800 milliamps and it will slowly start charging our cell. As the charging process continues, our voltage of the battery will increase automatically. And as you can see, the maximum charging current over here is 1000 milliamps or 1 amps, but it is also possible to configure our TP4056 to work on a lesser charging current, which I will tell you as we go along this video. So once it starts charging at 1 amps, you can see the battery voltage starts to increase, and when it reaches around 4.1 volts, the charging current will automatically start to decrease. So our IC, our TP4056 IC will start to monitor our charging current, and as the charging current reaches around 100 milliamps, it will terminate the charging process and say that the battery is completely charged. So this way we don't have to monitor our battery voltage or current, and everything is taken care by our TP4056. Now let's see how to connect this IC and make it work. We have our IC over here. The first pin is the temperature pin. So as I told you, there are three parameters. One is voltage, current and temperature, which can be monitored. But in this design, I have left the temperature pin as no connection because I'm not monitoring the temperature. But you can use an NTC and connect it to your battery to monitor the temperature. That way, if your battery is too hot or if it is too cold, there won't be any charging take place and your cell will be protected. And the second pin over here is the program pin, which, as I told you, decides the charging current. So the charging current can be set anywhere below 1 amps, and the formula to calculate your charging current, which is IC, is equal to 1 divided by R, which is the programmable resistor. So here I have used 1.2K, which will approximately give me 1 amps. So the formula is 1 divided by R into 1200. So 1.2K is 1200, so it will give me 1 amps. But if you want a lesser charging current, you can just change the value of this resistor and reduce the charging current. The third and the fourth pin are the ground and VCC pins. I am powering this IC directly from my 5 volts, which I will provide from a 5 volt mobile adapter, and the ground pin is connected to ground. And then if we come on this side, we have the battery pin, which is actually the output. As you can see, this is the output which is used to charge the battery. So this should be connected to the positive side of my battery. So another important thing is to take care of the polarity. Some batteries like this will not have the polarities written on it. Use your multimeter to find out which one is positive and which one is negative. Make sure you connect the positive of this. Make sure you connect the fifth pin of this IC to the positive end of your 18650. Then we have two more interesting pins, which is the standby and charge pin number 6 and 7. So what these two pins do is that, as you can see, these two pins are connected to an LED. We have 5 volts coming from here. And both of that is given through an LED and the current limiting resistor to pin number 6 and 7. So if the IC is in standby mode, the pin number 6 will be working like a ground, so this light will turn on. If the IC is charging, say for example if it is charging an 18650 cell, then this pin will go to ground and hence this light will turn on. So using this you can see whether the IC is charging or whether the IC is in standby mode. And finally we have the CE pin, which is the chip enable, which should be pulled high in order to make this chip work. If you want this chip to go into sleep mode and consume low current, you can pull this pin to ground using a microcontroller and this IC will no longer work. But for now I want this IC to be active all the time, so I have pulled it to 5 volts. Pulled it up to 5 volts. Now that is pretty much with the lithium ion battery charger IC. It's a very simple circuit, and over here if you see we have connected the positive of the battery to 5th pin and the negative of the battery is connected to the ground of our system. Now moving on, we will get into our 5 volt booster section, which is designed using the FP6291. So before we get there, let's take a look at the PCB. You can see the input port, which is used to charge the ICs over here. The TP4056 is over here, and the two LEDs which are connected to pin number 6 and 7 through these current limiting resistors are over here. And then we have some filter capacitors, and the 5th pin of the IC is connected to the positive, and the negative is connected to the negative pin over here. Now moving on to the booster section, you can see the FP6291 is a very small IC which is placed over here, and you only need a few extra components to design a booster circuit with this IC. So for this IC we will give input voltage from 3 volts to 4.2 volts. As I discussed earlier, the voltage rating of your 18650 cell will be from 3 volts to 4.25 volts. Once it reaches 4.25 volts, your charger IC will automatically stop charging it. So at any case, the input voltage that's going to our FP6291 will be from 3 volts to 4.2 volts. Now there are few things which you can configure for this IC. One is the output current and the other is the output voltage. Here I have configured this IC. We used to work with an output voltage of 5 volts and 1 amps. So let me show you how that is done. The first pin we have connected an inductor. So the value of this inductor could be between 3.3 microhenry to 4.7 microhenry. Using a drum type is a preferred value, but I didn't find a drum type, so I have used a normal resistor type inductor over here, which is of 4.7 microhenry. And then moving on, we have our overcurrent pin over here, which is connected to ground through a resistor. So earlier I didn't use a resistor here, which was a mistake, but I have corrected it. When you get the circuit diagram and design file, everything will be corrected and working, so you don't have to worry about this. So the thing is, on the 6th pin you have to connect a resistor to ground, and this resistor value decides the maximum current that will be going out from our FP6291 booster converter IC. So the formula to calculate the resistor value is equal to IC 48,000 divided by R. So I have used 47K as my resistor value, which will approximately give me a output current of 1 amps. So the maximum output current that this IC can provide is 2.5 amps. You can change the value of this resistor and increase the output current if required. And then coming down, we have a Schottky diode, which is for protection purpose, and then we have a resistor network. The resistor R1 and R2 works like a potential divider to give a feedback voltage to our feedback pin over here. So this feedback voltage decides the output voltage that we will be getting from pin number 1. So the formula to calculate the output voltage V out is equal to 0.6 into 1 plus R1 by R2. Here the value of R1 is 88K and R2 is 12K, thus we will get an output voltage of 5 volts. On the datasheet of this IC, you will also find this graph which gives you the current limit and the external resistance. So as I told you earlier, we have a formula to do that also. If you don't want to use the formula method, if you don't want to use this formula, you can directly check the graph. Say for example, if you need 1 amps, you need to use something like 48K. I have used 47K, which is approximately the same. So that's it, guys. The design is very simple. You could have even reduced the board size further if required, and as you can see, even there are no big complications in the PCB as well. So once you have finalized the design with all the required parameters, it's time to get your PCB boards fabricated. Mine has been fabricated from PCBWay, and I will tell you how to do that. To order your PCBs from PCBWay, just go into their website pcbway.com and you will be greeted with a page something like this. If you scroll down, you will find many interesting offers and competitions that are currently happening. But to continue with your ordering process, go to the top, make sure you have already logged in. If you're a new user, you'll also get a $5 coupon. As you can see here, you'll get $5 free prototype order. And to proceed with your order, just enter the dimensions of your PCB. Mine is, say for example, 50 cross 50, and I will need 5 numbers, and then click on quote now. On the second page, you will get few more interesting options where you can select the type of PCB, maybe a flexible PCB or an SMD stencil or whatever you want. In the bottom, you will find most of these you can leave in default as a 2-layer PCB. The material should be FR4. So most of these things you can leave it as default. But if you want to make your PCB a bit more interesting and colorful, you can change the solder mask color. For example, our PCB was yellow in color. The reason why PCBWay is cool is that you can change the different mask color. Even if I select an yellow mask, the price of the PCB is going to remain the same. For blue or red or green or yellow, the price is going to be the same. As you can see on the right hand side, the price is going to be the same. So you can play around with these options, and once you're done with that, you can see the build time for our PCB would be 3 to 4 days, and the shipping fee would be around $26. That is if I ship with DHL. You can explore other shipping methods and change the country to see which one would suit you. For example, FedEx is a bit cheaper than DHL, and you'll see the total value over here. Once you're comfortable with that, click on save to cart, and on the next page they will ask for the Gerber file. So the Gerber file for this project can be found at the link given in the description of this video. If you have a different Gerber file, you can also attach it over here. PCBWay also has a chat option where you can ask all your questions before you place the order. So I'm not chatting, so I'll close that down and then click on add Gerber file and just upload the Gerber. So once the Gerber is uploaded, click on submit order now, and after entering your address and completing the payment, within few days the PCB would arrive to your doorstep. After few days, I received my PCB in a neatly packaged box, and as you can see, the finish of the PCB is very good. The layers, the tracks, the wires, everything was neatly placed. You can directly proceed with assembling the board and testing it. Now, after receiving the board, I have assembled all the components on top of it, and I have my 18650 cell over here and the multimeter set in voltage mode for debugging purposes. So now let's power up the circuit and see how it works. I'm just using a normal 5 volt from any mobile charger. So if I connect it, you will notice that the orange LED goes on. The orange LED indicates that the chip is currently in standby mode and it is waiting for a battery to be charged. So once the battery is connected, the green light will turn on, indicating that the battery is currently being charged. So when nothing is connected on the output side, if you check the output voltage, it will be around 4.2 volts, which is the maximum voltage of our lithium charger IC. So now let me go ahead and connect the battery and see if the charging is taking place. Normally people solder these terminals directly to the battery, but it is not recommended to keep your soldering iron on a battery, and also be careful with polarities. I'm using magnets here because I don't have a spot welding machine with me. So once I connect my circuit, you can see that the green LED turns on, indicating that the battery is currently being charged. So this battery is almost fully charged. So if you check the charging voltage, it is around 4.15. So in another 2-3 minutes this battery will reach 4.2 volts and the charging setup will automatically go back to standby mode. That is, this green LED will turn off and this orange LED will turn on. So on the output side, the boost circuit will always be working. You can connect any device that is operating on 5 volt. For example, I can connect my TTL converter just to show you that we are getting output from the USB drive and it is still being powered. I also have an Arduino Nano with me with the default blinking program running in it. So let me connect this Arduino Nano board and show you how it is working with our booster module. I just have to connect it, and it is the programming cable used for Arduino Nano. And once I connect it, you can see that the LED on the Nano blinks because there is a basic blink program running on the Nano. I can even disconnect the circuit from the power, and you can see my Nano is still powered from the 18650 cell. Now of course, every time when you do it, there will be a reboot on the Nano side because there will be some voltage fluctuations, but as soon as you remove it, your Nano will start getting power from the 18650 cell and it will start working. And when the battery goes down, you can simply plug in the device and your charging will start working again. So that's it guys, this is how the project works. Hope you enjoyed the video and learned something useful from it. Thank you, bye bye.